Hey there. So picture this. It's the 1920s, a time of flappers, jazz, and, well, physicists completely losing their minds. They'd just discovered a whole new world, a microscopic one, and it was nothing like the world we know. It was chaotic, weird, downright impossible. And right in the middle of this scientific meltdown, one guy, Erwin Schrödinger, comes up with an idea, an equation. And this isn't just any equation, it's the equation that broke reality. No, seriously, we're still trying to put the pieces back together today. This single line of math, which looks like some alien hieroglyphics, psi of xt, doesn't just describe a particle, it describes a ghost, a possibility. It says that until you look, reality doesn't even exist. So what if I told you that the solid chair you're sitting on isn't really solid, that it's mostly empty space and a bunch of fuzzy, vibrating energy? What if I told you that in the quantum world, things can be in two places at once, or that a cat could be dead and alive at the same time? Sounds like science fiction, right? Like something out of a comic book. But it's not. It's science fact, and it's all because of this one equation. In this video, we're going to peel back the layers of this 100-year-old mystery. We're going to ditch the boring textbooks and the confusing jargon. I'm going to break it down in a way that actually makes sense, even if you haven't done math since high school. Stick around, because by the end of this, your view of reality is going to be, well, let's just say it might be a little bit broken too. Okay, let's start with what we know, the world we see around us, the classical world. This is the world of Isaac Newton, apples falling from trees, planets orbiting the sun. It's a world of rules, of predictability. If I throw a baseball, I can use Newton's laws to calculate exactly where it's going to land. It's like a giant cosmic clock. Everything runs on a schedule. You know where something is, you know how fast it's going, and boom, you know its future. Simple, right? Comfortable. It's the world that makes sense to our brains. But then the physicists decided to zoom in, like really zoom in, to the level of atoms and electrons. And let me tell you, the rules down there, they threw the rule book out the window. Imagine the atom like a tiny solar system. You've got the nucleus in the middle, acting like the sun, and then you've got electrons, which you might picture as little planets orbiting around it. That's what everyone thought. But when they tried to apply Newton's rules to these little electron planets, it was a disaster. The math didn't work. The electrons didn't behave like planets at all. They didn't travel in nice, neat orbits. They were everywhere and nowhere at once. It was like trying to track a hyperactive hummingbird with a faulty GPS. They'd be here, then there, without ever seeming to move between the 2 points. They weren't solid little balls. They were more like fuzzy clouds of probability. It was chaos. So the physicists are scratching their heads. Is an electron a particle, like a tiny marble? Or is it a wave, like a ripple on a pond? In the classical world, things are one or the other. A baseball is a particle. Sound is a wave. You don't see baseballs rippling through the air, and you don't see sound hitting you like a rock. But in the quantum world, it's like the universe is playing a prank on us. It's both, and neither, depending on how you look at it. This is called wave-particle duality, and it's one of those things that makes your brain hurt if you think about it too hard. It's like a person being both a solid object and a spread-out vibe at the same time. It just doesn't make sense in our everyday world. So, into this absolute mess steps Erwin Schrödinger. He's this Austrian physicist, a bit of a philosopher, a bit of a ladies' man, and a whole lot of genius. He's looking at this wave-particle mess, and he's like, okay, this is getting ridiculous. We need a new rule book. If electrons are going to act like waves, then we need an equation that describes them as waves. He basically took the idea of a wave, like a sound wave or a water wave, and he applied it to the world of particles. He wanted to find a way to predict what these fuzzy, unpredictable electron clouds were going to do. He wanted to bring some order back to the chaos. And that's when he came up with it, the equation. His equation. The core of it is this symbol right here, psi. It's the Greek letter psi, and it represents something called the wave function. Now, don't let the name scare you. A wave function isn't a physical wave like a water wave you can surf on. It's a mathematical wave. It's a description. It's like a recipe that tells you everything you can possibly know about a quantum system like an electron. But here's the kicker. It doesn't tell you where the electron is. It tells you where the electron might be. Think of it like this. In Newton's world, if I want to know where your car is, I can call you and you'll say, "I'm at the grocery store on Main Street." Bam, done. Location known. But in Schrödinger's world, if I ask the wave function where the electron is, it doesn't give me a straight answer. It says, well, there's a 40% chance it's over here near the nucleus, a 30% chance it's a bit further out, a 10% chance it's over there, and heck, there's even a tiny chance it's on the moon right now. It's not a precise location, it's a probability cloud. The wave function describes this cloud of possibilities. Where the cloud is thickest, that's where you're most likely to find the electron. Where it's thin, it's less likely. But until you actually go and check, the electron could be anywhere in that cloud. This is where it gets really weird. This is the part that broke reality. Schrödinger's equation says that as long as you're not looking, the electron isn't in any one specific place. It's existing in a superposition of all possible places at once. It's like spread out like a wave of probability. But the moment you measure it, the moment you interact with it and say, "Hey, where are you?" the whole thing changes. The wave function collapses. All those probabilities, all those might-be's, they instantly vanish, and the electron is forced to choose one single location. It snaps into reality. It's like the act of looking creates the position of the electron. Before you looked, it wasn't there. It wasn't not there. It was just a cloud of maybe. Okay, I know what you're thinking. Hold on a second. Are you telling me that things don't exist until I look at them? That the moon isn't there when nobody's watching? It sounds completely bonkers, right? I mean, it goes against everything our common sense tells us. But this is what the math is telling us. This is what the experiments are telling us. The quantum world doesn't play by our rules. So I want to hear from you. Pause the video for a second and drop a comment below. What's your immediate reaction to this? Does it make your brain hurt? Do you think it's cool? Or do you think the physicists have just lost their marbles? Let me know, and then we'll dive into how Schrödinger himself tried to make sense of this madness. So, you'd think Schrödinger would be thrilled, right? He just revolutionized physics. He's a hero. Nope, not even close. He hated this interpretation of his own work. He was a classical guy at heart. He believed in a real, solid universe, not one made of fuzzy probabilities that only become real when you look at them. He thought this whole collapse idea was ridiculous. He famously said, "I don't like it, and I'm sorry I ever had anything to do with it." He wanted to show just how absurd this idea was, so he came up with a thought experiment. You've probably heard of it. It's about a cat. Okay, here's the setup. You take a cat, a theoretical cat. No actual animals were harmed in the making of this physics dilemma. And you put it in a sealed box. Inside the box, you also have a nasty little Rube Goldberg machine. There's a tiny speck of radioactive material that has a 50% chance of decaying within, say, an hour. If it decays, it triggers a Geiger counter, which releases a hammer, which smashes a vial of poison gas, which, well, it's not good for the cat. If the atom doesn't decay, nothing happens, and the cat is fine. So you seal the box and you wait an hour. Now, here's the question. Before you open the box, what is the state of the cat? According to our everyday logic, the cat is either dead or it's alive. It's one or the other. We just don't know which one yet. But according to quantum mechanics, according to Schrödinger's own equation, the radioactive atom is in a superposition of being decayed and not decayed. And since the cat's fate is tied to that atom, the cat itself must also be in a superposition. The wave function of the cat describes it as being both dead and alive at the same time. Not one or the other, both. This is what Schrödinger was trying to point out. He was like, "Look, guys, this is insane. A cat can't be dead and alive at the same time. That's just not how the world works." He was trying to use this example to show that there must be something wrong with our understanding of quantum mechanics, that we can't just apply these weird microscopic rules to big everyday objects like cats. But the irony is, this thought experiment, which was meant to disprove the idea, became the most famous illustration of it. It showed that if you take quantum mechanics seriously, you have to accept some pretty bizarre consequences. It brings the weirdness of the micro world right up into our macro world. So, where does that leave us? For decades, the standard answer was the Copenhagen Interpretation, which is basically the shut up and calculate approach. It says, yeah, it's weird, the wave function collapses when you look, don't ask why, just use the math because it works. And it does work. It's the basis for almost all of modern technology. Your phone, your computer, lasers, MRIs, none of them would exist without Schrödinger's equation. But a lot of physicists, like Schrödinger himself, were never satisfied with that answer. It feels like a cop-out. And this led to other crazy ideas, like the many worlds interpretation. This one is even wilder. It says there is no collapse. When you open the box, the cat doesn't randomly become dead or alive. Instead, the entire universe splits into two copies. In one universe, you open the box and find a dead cat. In another, equally real universe, you open the box and find a live cat. Every time a quantum event has multiple possible outcomes, the universe splits to accommodate all of them. So there's a nearly infinite number of yous living out every possible variation of your life. It solves the collapse problem, but it creates a many worlds of madness. We may not have all the philosophical answers yet, but one thing is for sure, Schrödinger's equation is the key to our future. We're now moving from just understanding the quantum world to actually controlling it. We're building quantum computers that can solve problems in seconds that would take today's best supercomputers thousands of years. We're developing quantum encryption that is unhackable. We're designing new materials and drugs at the molecular level. The equation that broke reality is now helping us to build a new one. So, there you have it. Schrödinger's equation, a simple line of math that opened up a universe of ghosts, probabilities, and dead and alive cats. It's a 100-year-old mystery that we're still unraveling. It reminds us that the universe is far stranger and more wonderful than our everyday experience would have us believe. And that's the beauty of science. It's not about having all the answers, it's about asking the right questions. If you enjoyed this journey into the quantum rabbit hole, hit that like button and subscribe. We've got plenty more mind-bending science coming your way. And let me know in the comments, which interpretation do you prefer? The collapsing wave or the many worlds? Thanks for watching and keep looking up.